Somewhere in the Arabian Sea, at 2 in the morning, a Tomahawk cruise missile clears the deck. This is cell number 96, firing the final shot into an IRGC command node buried inside the Zagros Mountains. The target is destroyed. Right now, this $2.5 billion destroyer is completely intact. The crew is fully rested and combat ready. Yet the ship is swinging its bow away from the coastline and heading south, directly away from the fight. It is leaving because of what sits beneath the deck. There are 96 vertical launch cells on an Arleigh Burke destroyer. After that last strike, every single one of them is empty. This warship is designed for absolute spectrum dominance, carrying the most advanced combat system ever put to sea. But out here on the open ocean, it cannot put a single new missile back into those tubes. Without a machine to reload it, the ship is tactically irrelevant. To refill a vertical launching system, or VLS, you need rigid infrastructure. You need a concrete pier and a heavy shore-based crane that is firmly bolted to bedrock. For a destroyer operating in the Arabian Sea, the nearest available crane is nowhere close. The closest guaranteed facility is over 2,000 nautical miles south at Diego Garcia. The math on that transit is brutal. It takes 1 full week to sail there, 3 to 5 days sitting under the crane to reload, and another week to sail back. That is 3 weeks completely out of the combat zone. If a fleet has 10 destroyers on station burning through their magazines, at any given moment, a third of your force is trapped in transit, and another third is queued up at a pier. The United States Navy possesses unparalleled firepower, but when firing your weapons forces you to abandon your post for 3 weeks, you create a massive presence problem. To understand why a modern Navy cannot simply reload its own missiles at sea, look at the physical dimensions of the cargo. You have to lower an incredibly volatile, massive cylinder into a narrow steel sleeve, all while standing on an unstable surface. A Tomahawk cruise missile inside its launch canister weighs 3,500 pounds and is over 20 feet long. The VLS cell receiving it is a steel tube roughly 25 inches square. That leaves just inches of clearance on each side. This wireframe diagram demonstrates the oceanic forces acting on a ship's hull. On the open water, the vessel moves across 6 distinct axes simultaneously. You have pitch, roll, and heave, alongside yaw, sway, and surge. Every second, the deck shifts. When you suspend a 3,500-pound canister from a flexible crane cable in these conditions, you create an uncontrolled physical oscillation. The ship rolls one way, the heavy canister swings the other way. Even in moderate swells, the amplitude of that pendulum swing quickly exceeds the tight clearance limits of the VLS tube. The canister inevitably drops off center and violently strikes the inner steel wall. Steel meets steel. Inside that canister is a warhead packed with high explosives and a solid rocket booster filled with propellant. A single uncontrolled impact creates an immediate evacuation scenario. The Navy didn't stop trying to reload at sea because of a lack of effort. They stopped because the uncompromising physics of the ocean made standard cable cranes mathematically impossible to use. Naval architects originally tried to work around this. Early Flight 1 and Flight 2 Arleigh Burke destroyers were built with internal strike-down cranes. Each crane module took up the space of 3 missile cells, lowering the ship's total capacity from 96 down to 90. But those internal cranes lacked the heavy load rating required to handle fully armed Tomahawks. They were only usable in perfectly calm seas, a condition that rarely aligns with actual combat deployments. So, starting with the Flight 2A destroyers, the Navy made a hard trade. They removed those cranes entirely and filled the empty space with 6 additional VLS cells. In 1999, that trade-off made perfect sense. The strategic assumption was that future conflicts would be brief, precision strikes would be highly surgical, and 96 missiles would easily be enough to finish the job before the ship ever needed to return to port. By optimizing the architecture to maximize initial firepower, the Navy permanently compromised its ability to sustain a long attritional fight. The fleet already conducts underway replenishments, transferring fuel and food between ships steaming side by side using tensioned cables. But standard cargo can tolerate rough handling. A 20-foot precision missile containing volatile propellant cannot be caught in a cargo net or rolled aggressively across a steel deck. To solve the kinetic equation, engineers at the Johns Hopkins University Applied Physics Laboratory designed a device called TRAM the transferable reload at sea method. This schematic details how TRAM works. It eliminates the pendulum completely. Instead of suspending the missile from a swinging cable, the device clamps the canister in rigid hydraulic jaws, locking it directly to the rails of the VLS module. Because the missile is now physically connected to the exact same frame as the cell, relative motion drops to zero. The ship moves, the rail moves, and the canister moves together as one rigid body. The mechanism smoothly rotates 90 degrees and slides the weapons straight down. Real-world testing off San Diego in late 2024 and aboard the USS Farragut in 2025 validated the engineering, proving the system could achieve the high-speed reload rates required for sustained combat operations. By eliminating the physics of the pendulum, TRAM compresses the 3-week logistical round trip into a 4-hour replenishment pit stop. But when we test this new logistical capability against the high-intensity combat tempo of a scenario like Operation Epic Fury, a new friction point emerges. Over the course of 12,000 strike sorties, American destroyers and submarines launched 850 Tomahawks in less than 5 weeks. The strikes were devastatingly precise. The ordnance systematically dismantled enemy airfields, eliminated command nodes, and cratered naval bases deep inside heavily defended territory. This volume of fire uncovers a critical strategic gap. While TRAM can move missiles to the front line with incredible efficiency, the device itself has no way to manufacture the weapons it reloads. The platforms on the front line are firing highly advanced munitions at a speed that vastly outpaces the supply chain's ability to push replacement weapons to the replenishment ships. The efficiency of American tactical firepower has successfully outrun the exact industrial system designed to sustain it. Compare that expenditure directly against the defense industry's manufacturing baseline. Firing 850 missiles in 35 days creates an immediate deficit. This chart illustrates the production bottleneck. On the left, the fleet burned through 850 weapons in just over a month. On the right, we see the defense industrial base, which currently produces roughly 60 to 90 Tomahawks per calendar year. Building a modern precision munition is immensely complex. You are assembling a turbofan engine, guidance sensors, and high explosives. Each unit requires thousands of precision components sourced from over 100 different subcontractors. That creates an irreversible time constraint. It takes 18 to 24 months of metal tooling and manual labor to build a single weapon. It takes a destroyer 12 seconds to fire it. You cannot simply release a software update to scale a physical factory. Ramping production requires heavy machinery, teams of trained engineers, and massive supply chain overhauls. The physics of manufacturing do not accelerate just because a combat scenario demands it. The unyielding physics of metal, heat, and time on the factory floor dictate the ultimate capacity of naval power, far more than the launch cell or the reload crane. Now, picture that $2.5 billion destroyer heading south in the middle of the night. With the TRAM system installed, that ship no longer has to retreat to a concrete pier. We solved the pendulum effect. We engineered the heavy hydraulics needed to safely reload an active warship at sea, effectively closing the presence gap. But when the mechanical reload is solved and the fleet can empty its magazines in a matter of days, we face a harder question. Who is building the ammunition to keep them in the fight? We have built a force capable of instant, overwhelming lethality, tethered to a supply chain that measures replacement timelines in decades. Industrial machines capable of mass-producing munitions determine the winner of a high-intensity conflict, carrying more strategic weight than the multi-billion-dollar platforms designed to fire.